Eric, can you make sure you have started the recording?
Yep, I'm checking here. Yep, we're recording, so we're good. So I'm just going to pause for a second because we're not quite 2:15, but we're really close here. So
Okay.
You can go ahead.
all right, so for our final speaker in this session, we have Emily Haase from University of Minnesota Duluth talking about investigating cosmic ray muons and their velocities. Emily, go ahead and take it away.
Thank you. Hello and welcome to my talk about muons and their velocity. First, a little bit about me. My name is Emily Haase, and I am originally from Spearfish, South Dakota. It's a small town about a stone's throw away from the Wyoming border. Currently, I am a junior at the University of Minnesota Duluth, and I am majoring in math and physics. So what are muons? Muons are an everyday part of our life. They were first discovered in 1936 by Carl D. Anderson and Seth Nettermeyer, and they're elementary particles that are produced by cosmic rays colliding with particles in the Earth's upper atmosphere, as nicely depicted by this graphic in the right-hand side of the screen. The muons are represented by the solid red line with the Greek letter mu next to them. Muons are most comparable with electrons, but their mass is about 200 times greater, and they're much more penetrating. They can penetrate up to tens of meters into the ground. They have a 2.2 microsecond lifetime in their rest frame, and they comprise about half of our natural background radiation. The other half is comprised of other sources of radiation, such as X-rays and radon. Most importantly for our talk today, muons have a velocity of the speed of light, which is about 3.0 times 10 to the 8th meters per second. So for my experiment, I'm trying to detect muons and then confirm that their velocity is the speed of light. So to detect muons, I use a muon telescope that is comprised of 4 scintillators. One of the scintillators is shown below in this graphic. They are about the size of a laptop, and they're wrapped with black tape and black plastic to keep out light, because that can really make for some noisy data. And the experiment is defined by 2 main setups that are defined by their overall distance between the first and last scintillator. So the first setup is 0 meters. So you just stack all the scintillators one on top of the other, and that's called the calibration setup, which I will discuss more later. The second setup is shown here on the right, and it's 5.5 meters between the first and last scintillators. In this photo, you can see the orange arrows are pointing to each scintillator. You can kind of see a little sliver of black, and that is a scintillator. You can't see this one because it's beneath the table, but we call the scintillators channels. So this is channel 0, channel 1, channel 2, and channel 3. And so what we're trying to do is we're going to measure the velocity using the equation velocity equals distance over time. So we measure these distances, and the overall is 5.5 meters. And then we're going to try to take some time differences and then calculate the velocity. So for example, for a muon going to speed of light, it will take 16.5 nanoseconds to travel to 5.5 meters. This setup is also currently in the atrium in the library annex, which is closed for COVID. That is kind of useful because it's relatively undisturbed, so we can just let it run for 2 weeks and collect hundreds of thousands of events. Calculating the mean time difference. So when we get the data from the DAQ card that is connected to the scintillators, it comes in this form here in this graphic in the upper right-hand corner. It's in hexadecimal, which is not very user-friendly. So we run this data through another program that unpacks the data and makes it more user-friendly, which is nice. If you look at this first column, the slightly grayed out numerical value is the event number. So each row is an event. And so you can see in this file, there are approximately on the order of 500,000 events in this file. So we get quite a few. In the third column here, you see there's a numerical value of 3 or 4. What that means is that 3 or 4 scintillators are active. And then in the next column with these 4 digits, it's telling you which ones are active. So in this first row, this first 0 corresponds to channel 0 up here. So this is from the previous slide. You can see the setup. And so this means that it missed the first channel and then hit channel 1, channel 2, and channel 3. Likewise, in the second row, it's saying it hit channel 1, channel 0, channel 1, and channel 2, but missed channel 3. And so 3 hits or 3 scintillators being active is good, and it's most likely muon, but we really want 4 because it's just better data, and it's really more likely muons. So we like 4 hits. And so if you look down here in the last row, you can see that the fifth column says C0, which is just for channel 0, and it's just defining the next 2 rows. So the next row after that is the start time, and then the row after that is the end time, and that's the same for each of the channels. And if we want to unpack this a little more, you can see that channel 1 has a start time at 30, and channel 2 has a start time at 49. The difference between those is 19 ticks, and what that means is that is the time it takes for a muon to travel between C1 and C2 is 19 ticks. And 19 ticks is not a one-to-one comparison to nanoseconds. It's about 1 tick is 0.75 nanoseconds, so it's not directly 19, but we'll just use 19 ticks for now and unpack that later. In the final column, you see this huge number, and this is an internal clock that has units of 24 nanoseconds. And what it does is it's keeping track of the start time of each event. So it's keeping track of when the event happens, so we can use that to determine the time between events. And so I did a little calculation down here that you can follow along with. So this is about 900 million, and we can subtract that from 700 million, and then we get about 200 million. And we multiply that by the units of 24 nanoseconds and get 5 billion nanoseconds approximately, which is just 5 seconds. So all this means is that every event is happening every few seconds or so. So once we get the data, we make selection cuts on it to isolate the muons and the muon-like data in order to get better data and more precise data. So you can see on the left, on the right here, this is an oscilloscope, and on here is a pulse. So what happens is when a muon goes through a scintillator, it leaves a deposit of energy, and that energy is defined by the start and end time, because that defines really how large the pulse is. And relatively speaking, compared to other noise that may activate the scintillator, muons leave a larger deposit of energy. And so if you look at this single pulse, this is actually from channel 2, you can see that where the purple pulse passes the red one, that's the start time. And the second time that happens, that's the end time. So this is the single pulse. It's about 40 nanoseconds wide. And then this graphic down here in the left corner is a distribution of the time durations for a sample size of approximately 130,000 entries. So really short pulses give a lot less precise data, and really large pulses are likely to be multiple particles. So I will get this distribution, and in the actual program, I will program it to be around between 30 and 60 ticks. And that's not very useful. We like nanoseconds, so I wrote these above the 20 and 80, so it gives you a little more perspective. So we want to restrict the event duration so we can get the bulk of the peak and isolate the muons. So this pulse most likely falls somewhere in here around 40. It's not an exact one-to-one because this is nanoseconds and this is ticks, but it's about right there. You can see it's right about in the peak of the distribution, which is where we want it. So time difference Gaussian distributions. Gaussian normal distributions are one of the most important distributions in statistics. They're the most likely distribution for most experiments. So most experiments, when you take the data, it just kind of falls into a Gaussian distribution. And that's what we expect for our experiment as well. So we expect our data to be Gaussian-like. You can see on the right graphic here that this is an example of some of our data. It's a little bit smaller. It's only about 30,000 entries. But you can see the data is represented by the green line, and then the Gaussian fit is the continuous black line. And you can see that it fits relatively well. So we're happy about that. And you can calculate the standard error and the mean by taking the standard deviation, which we have up here in the top right corner of the graphic, divided by the square root of n entries, which we have up here as well. And so for this distribution sum, we can calculate the standard error on the mean using the sigma of 3.279 and the entries are 29,296. And we can see that we get about 0.019 ticks, which is about 0.014 nanoseconds. So this is the ultimate precision that we're hoping for. Small spoiler alert, we don't have this yet. This has not happened in our experiment. And we'll talk about that more later on. So we have the mean time differences, and we have the distances that we measure. So now we can calculate our velocity. So earlier I talked about the calibration setup, which is 0 meters. And the reason this is important because each scintillator has a different cable length. And so there's timing offsets due to those cables because the data is carried back differently due to the lengths. And so to correct for that, we put it in a calibration setup for the 0 meters so you aren't calculating the velocity because the distance is 0. The distance is 0. And so we're just measuring that timing offset in the calibration setup. So then we can take this mean to T2 C1 and that's 20.8, and we subtract off the calibration mean to account for that time delay, and we get this difference. But this is in ticks, and we want nanoseconds, so we convert it over by multiplying by 0.75 nanoseconds, and we get 11. And then we have our time difference and our distance, and we can calculate our velocity. We expected value of 0.3 meters per nanosecond, but as you can see, we're getting higher than the speed of light, which is physically impossible. So obviously there's some kind of error going on in this experiment. So systematic anomalies in the calibration data. We have a hypothesis that the anomaly is in the calibration data. As you can see in these Gaussian distributions and these graphics, a lot of our data has these systematic anomalies, these artifacts within the data that is skewing our mean, and so it's skewing our overall velocity calculation. When we apply selection cuts, so this graph on the right has no selection cuts and the graph on the left does, you can see that the artifact is reduced, but it is not gone. And so it speaks to some systematic effect within the experimental setup or the apparatus itself. What does this mean? It means moving forward, we have a few hypotheses about what could be the problem, but we have to do some more testing and diagnostics in order to correct that problem and figure it out. And hopefully that will be pretty soon. I will take any questions you have.
Great, thank you, Emily. Let's open up the questions from a number of folks. I will have one in a second here, but let's take one question from the room first.
So first of all, really good talk. I enjoyed it. Okay, so the hypothesis, if I understand correctly, is that these muons are traveling at the speed of light.
Yes.
Okay. How long do we talk about them having a lifetime in their own reference frame if they're
the lifetime, in their own rest frame. So muons are technically, their lifetime is so short that they should never be able to reach Earth. But thanks to special relativity and the difference in reference frames, they can reach the ground. And so that's why I had to clarify within their own rest frame, because.
Right. Okay, so are they, or is the idea that they're moving very close to the speed of light, but they are actually experiencing time? Or?
Yeah, so they're so close to the speed of light, or nearly or at the speed of light, that we have to be relativistic in our calculations. Okay. Is that what you're asking?
I think.
Okay.
And then also your detectors are sensing the muons, like individual muons at different sensors, so you're able to like see them without destroying them or absorbing them.
Yeah, so what happens is basically the muons will pass through a scintillator and they'll interact with the particles in the scintillator, and that interaction leaves behind some energy. It doesn't really affect the muon itself too much, but it allows us to realize like, oh, a muon passed this way because of the energy that it deposits is somewhat unique. And so when it passes through all the scintillators, we can see that and realize like, oh, this is a muon. And so that's how we're able to track it, but it doesn't really have a huge effect on the muon. Like, it does lose a little bit of energy, but it's not enough to seriously affect the calculations or the muon itself.
Could you go back to your slide that had the table of channels on it?
Yes.
Yes, this slide, one forward from this. Yes, so at the bottom there, why is it that channel 1 has a 30 and channel 0 has a 31, and then channel, in other words, it almost looks like channel 1 goes off after channel 0, and similarly, it almost looks like channel 3 goes off after channel 2. Why is that?
Right. It's not very physical. The reason for that is because
cabling length, is that what you're talking about?
Yeah, that is a part of it, is that there's like fluctuations in the data, and that this isn't necessarily an exact, there's fluctuations on, so like when C2 has a start time of 49, it really has, it's within a certain interval of maybe like 48 to 50. So that is part of it, but it is also due to cable delays and the fact that C2, channel 2 has like about a 1 foot cord cable, and the rest of them have on the order of maybe 20 to 30 feet of cables. And so just the cable delays and the fluctuations in the data itself just lead to some of these unusual data in which, like, you know, channel 3 is 47 and channel 2 is 49. That doesn't mean that the particle is popping through channel 3 and then backtracking through channel 2. It's just that there are just inherent fluctuations within the actual data, and that's why we have to account for those in our final calculations.
What about the duration? I mean, the duration in channel 0 seems to be so much shorter than the duration in channel 1. Does that bother you?
Thank you. I was just going to ask that too.
From 31 to 52, and then from 30 to 67.
Yes. Yeah,
Is that-
I mean, it does bother me. You are right, but I think that is also just I think it goes back to the fluctuations in the data, in that the scintillators are unique in some ways. And so the way that they report data is sometimes just like, as long as the peak structure and the Gaussian structure is there, the means may be somewhat different just because of the way that it's reported. But as long as the Gaussian peak is there and they all look pretty similar, then I think the structure speaks to the fact that it's good data.
Okay.
For the duration, you can go to your slide that shows the distribution of duration, and then the same answer applies, but they can see the graphic of what fluctuations happen in the duration.
In this one. Yeah. So yeah, so you can kind of see, like, on this one, this is the distribution of the durations, and there are like some fluctuation, especially like in the tail and stuff. But I think it's the fact that the overall peak has a good distribution that is the important part, and that it seems like a reasonable distribution. Any other
I'm trying to
questions?
remember, so I'll ask a question too. So I know one needs to get, for the statistics right, you want to leave it running for 2 weeks for that. Have you all done shorter runs, and what type of variance do you see, sort of like in a 1 week versus a 2 week run, in terms of the number of events? I know that cuts down on your N number and that screws up your, right, you know, but what kind of variance do you see potentially there? That's always a question that I guess I've never had answered.
Variance in the data itself, or variance in like the anomalies, or?
Yes, both.
Both. Okay. So in this graphic, especially, this is 30,000, which is pretty low. This is only a couple of days worth of data. Usually we like to have a week or two, which is on the order of, you know, hundreds of thousands, maybe even 1 million, depending on what setup we do. And so the difference in smaller amounts of data, the anomalies seem more pronounced just because there is less entries. And so there's less of a bulk to take away from those and offset those anomalies. So that's definitely present. As far as if it's an actual Gaussian distribution like this one, then it doesn't seem to have any anomalies. I believe it's only the scale that really changes, just the amount of entries that are present. It doesn't really change the overall distribution.
Thank you.
So thanks, Eric. Why don't we wrap this up, and why don't you post that link for people to chime in on their favorite presentation?
Yep. So